And good morning again. My name is Mark Adelsberger, and I'm with IPM Institute North America. And our first presentation is going to be Dr. Laura Johnson with the National Center for Water Quality Research Lab here at Heidelberg University. Thank you.
Good morning, everyone. How are you? I'm here to start everything off talking about our tributary loading program and some of the results that we have and some of the soil sampling we've done. And I take it a couple steps farther than that, and hopefully it'll foster some thoughts to lead into the rest of the talks for today and tomorrow, as a matter of fact. All right, so let's start at the very beginning. Instead of having a whole lot of introduction, I thought I would just jump right into our tributary loading program. For those of you who are unfamiliar with it, probably those of you who are familiar with it, you get to just learn that I say the exact same words over and over again every time I give these slides. So this is a map of our sampling stations. Each little red dot is where we're actively collecting water samples. Here on campus, we have Rock Creek. So if you're wondering where you are, because you didn't look very closely at your Google Maps, then we're right here on Rock Creek, which is in the Sandusky River watershed. Now, our lab started in sampling the Sandusky River watershed. It's kind of our baby. So we've been sampling there for the longest period of time. But following the sampling in 1969, we started doing the more high-frequency official sampling in 1974 with the Maumee, the Sandusky, and technically the Portage as well, although we didn't maintain that for the long term. We re-added that back in 2011. So those are our longest-term stations. After we had those, we added in other stations like these subwatersheds to the Sandusky, the River Raisin, the Cuyahoga. In the mid-90s, we added the 3 tributaries here that go into the Ohio River and ultimately the Gulf of Mexico. And then the other location that I haven't talked about is around Grand Lake St. Mary's. Grand Lake St. Mary's is Ohio's largest inland lake, and it has some algal bloom problems as well, so we do a lot of monitoring around there. Each station is paired with the USGS gauge. So we get water quality. We need USGS to be able to get the really good flow data. They're the ones that tell us whether the rivers are flooding or not, right? And so we put that data together to get our loads. So our goal here is quantifying watershed loads. What we want is to know is the export of those pollutants out of the watershed, and that's why we sample so very, very often. All right, so if you went to one of those red dots, you'd see a building by the river. It looks kind of like this, an anonymous shed. It doesn't have lawnmowers in it on stilts for some strange reason. Instead, it has a water sampler. So if you jumped in the water, you would see a pump that's pumping water into the building continuously. It goes into a sink that essentially is a flow-through system, so there's a drain and it drains back out. We sample the water that collects in the sink using an automated sampler. So, it samples 3 times a day, and we put the bottles are then stored in this little mini refrigerator. So this is like the size of a dorm room refrigerator, but instead of having beer in here, we have water samples. Right? Like I said, we collect these samples 3 times a day. We analyze all 3 samples if flow is up or if the water is turbid. Otherwise, we analyze 1 a day. The only time we miss samples is if things break, which happens sometimes. Sometimes things freeze. Sometimes these pumps get clogged. Sometimes floods decide to deliver the pumps way up onto the shore. Anything can happen. So our samples are collected every week on Mondays. You can see a picture of Jake here collecting samples in the winter, and brought back to the lab for analysis of just about everything. So we analyze major forms of phosphorus and nitrogen using a variety of techniques. We measure suspended sediments, how much mud is in the water, essentially. And then at some of these watersheds, we're also monitoring for pesticides. Okay, so I first wanted to jump in and talk about what we're finding. Well, I'm going to focus on Lake Erie, so we can cut off like the rest of the watersheds, right? But I wanted to start with the Maumee River because we always talk about the Maumee as being, oh, that's what's driving everything that's happening in Lake Erie. But part of the reason is because it just happens to be the biggest input, especially into the western Lake Erie basin. But if you look at the phosphorus coming from Maumee compared to all of the watersheds across all of the Great Lakes, it's the largest tributary into any of them. So looking at patterns here tell us a lot about what's been happening over time. So what have we found? Now this is showing our long-term trends in phosphorus concentrations We have total phosphorus up here, dissolved reactive phosphorus down here. And I put these little pictures to remind you that total phosphorus is if we collected that water sample, it's got the mud in it, it's got the dissolved stuff in it, we get all the phosphorus associated with all of that. But we can filter out these particulates on a piece of filter paper, and whatever makes it through is what's dissolved. Okay? We do that because the particulate phosphorus is not as easy for algae to use as the dissolved phosphorus. Works the same way in crops. You know, if you have plant available phosphorus, it's usually more dissolved than the particulate bound. So what have we found? Well, total phosphorus has declined slightly over time. Most recently, we see a little bump up and then maybe a slight trend down. This is in terms of an annual concentration. But dissolved reactive phosphorus is where we see all of the changes, right? We see that it was high, we dipped down to the mid-90s, and then we increased, and now we stayed basically high again. And this pattern eerily corresponds to when we had algal blooms in the lake, and then when we didn't have as many algal blooms in the lake, and then when all the algal blooms returned to the lake, right, when you think of the timing for that. So, you know, this twofold increase is what we're really concerned about. But because I figured there are some agriculture types here, you might be really interested in what's been happening with nitrate, I thought I'd throw that up there as well. So these are nitrate trends, and you can see this is more hump shape. Since around 2000, nitrate has actually been trending down. It's maybe starting to level off. We need a few more years of data to see if that's the case. Okay, so I'm going to focus first on dissolved reactive phosphorus because that's where all our changes are occurring. And the first question you'd say was, well, it's great that you find that in the Maumee, Laura, but I'm wondering if you find that anywhere else. So there's the Maumee, showing you that this is a reminder of what it looks like, right? But let's go to the Sandusky. And the Sandusky River is somewhat similar to the Maumee. 78% agriculture, Maumee is 72%. Types of agriculture fairly similar. Not very many large towns, so on and so forth. And we see the exact same pattern, right? That same U-shaped pattern. We can move up to the River Raisin in Michigan. We see the same pattern, right? That same increase, but now we're on a different scale. River Raisin does not have nearly as high concentrations as the Maumee or the Sandusky because it doesn't have as much agriculture and it's draining more sandy soils. So water just runs off differently. But then we can look into some of these sub-watersheds. We have a couple of them here in the Sandusky. Let's look at Honey Creek, and you can see Honey Creek, it's not so much a U-shape, but almost like a hockey stick. We have this big increase that's happened. We don't see as big of a decline early on, probably because we don't have as many municipalities in part, but we've definitely seen a big increase, and our scale is much higher. So now 0.5 is down here, and we're higher than anything we see in the Maumee or the Sandusky. So big increases in Honey Creek. But all of these cases are talking about highly agricultural watersheds with very few towns or municipalities, but you could still make the case that, of course, people are still living here. You know, is it agriculture, is it not? But we have had some long-term monitoring on the Cuyahoga. Cuyahoga has very little agriculture. It's almost completely dominated by point sources, and you see a totally different pattern. We see this big decrease early on. This occurred because the big push early on was to control point sources, get phosphorus out of our wastewater and getting into the lakes. And that's been highly successful, and you can see an example of that in the Cuyahoga. There's a little bump here because of increased population growth, but since then, around 2000, we've been seeing decreases in dissolved phosphorus from the Cuyahoga. I should have mentioned that this is upstream of Cleveland, where we're getting all of Akron's point sources, right? And there's a lot of residential areas if you've been around the Independence area where our station is. Okay. I also wanted to point out on the Maumee here, you see this line where things are low in the mid-90s? That is the current target reduction, concentration, what we're going for to reduce the occurrence of harmful algal blooms in Lake Erie. It happens to correspond, it was determined using lots of models, happens to correspond with this period of time when we had fewer blooms. So ecologically, in our brains, it makes sense as well. I also wanted to show you nitrate, again, because I think it's interesting. So remember I showed you there's this decrease in Maumee's nitrate since 2000. Same thing in Sandusky, maybe even a little bit stronger. Same thing in River Raisin. Same thing in Honey Creek. So all of these watersheds, we see these increases in dissolved phosphorus, we're seeing the same decreases in nitrate. So I think that's really interesting. The Cuyahoga River, really hasn't changed that much. You could say it looks like a decrease, but notice how different the scale is here. We're talking about much lower concentrations of nitrate overall. Okay. So when we look at the loads of phosphorus, so we take that concentration, we multiply it by discharge, so we get the mass of phosphorus coming out of these rivers. When we look at these loads from the Maumee River, we've noticed that no matter what type of phosphorus we're talking about, since about 2003, whether it's total phosphorus, dissolved phosphorus, take two of them and make a total bioavailable phosphorus, they all correspond very strongly with discharge, right? Everything sort of varies similarly. And this is in part because when I showed you that curve, when we get to the past decade, we've leveled off in concentration. So what's driving changes from one year to the next is rain, right? Does it rain a lot? Yes, we have a big bloom. Did it not? No, we didn't have a big bloom. So this suggests there's a strong hydrologic control in runoff. This is why we can forecast the blooms fairly well. And what this is indicating to us is that what's coming off in terms of phosphorus is chemostatic, meaning there's a large source present. Every time it rains, we get an increase in phosphorus, right? And so here's an example of that. This is 2015. The blue here is just showing flow, right? So you see big storms, lots of storms through June and July. This is that really, really big bloom year because of all of these storms. And when we look at DRP concentrations, dissolved phosphorus concentrations, we see that essentially for every storm we see increases. The opposite of what we would expect would be like what we would see for something like nitrate, where nitrate gets applied and it runs off. And here's an example here. So for nitrate, we see early on there's actually dilution of nitrate because there's so much water it's diluting what's coming off the land here. But the applications would have occurred in May, mid to late May. And then you see this huge peak of nitrate from this relatively small storm compared to the rest of them, right? But then when we had these big storms, we didn't see any more increases because that pool of nitrate is getting depleted because it's not chemostatic, because it's a big source for a little while, but it doesn't last for very long. So we can see these differences, and it tells us a little bit about what's happening with phosphorus coming off the land. But I don't want to ignore the fact that we do see what I would call acute runoff of phosphorus in some instances. If that happens, we can see it fairly well. So this is Honey Creek. And what we're showing here is the 2012 water year. It happens to be 2011, because that's how water years work. Again, the blue is discharge. And you can see we've had some big peaks in phosphorus. Now remember before I was showing you these ranges were much, much lower. We're talking about peaks getting up to the milligram per liter range. In a creek, this is like the limit for wastewater treatment effluent. These are really, really high concentrations. And we noted that these all occurred when we had fertilizer application occurring right before the storm event. So you apply fertilizer, it rains, it washed off, and we see it, okay? So this does happen, and we can pick it up, and I can show you an example of what that would look like. So I'm gonna show you lots of years of Honey Creek, starting again with 2012, right? So this period of time here now is this smushed in, right? What we notice is that when we look over the whole year, for most storms, we see about the same increase unless it's an acute runoff period, right? So we're getting up to about 0.2 milligrams per liter. It seems like plus or minus a half a milligram, I would say, for each storm. And it lines up like this here. So that's 2012, but here's 2013, and 2014, and 2015. And you could argue, well, here's another period of possible acute runoff where that fertilizer is applied, and we got a small rain event, and it probably ran off. 2016, same thing. We didn't get any rain after, I would say, June, right? There's hardly any changes. But the rain that we did get got up to about the same concentration. So we're seeing this possible large source of phosphorus in soils. Okay. So why did this happen, and why do we have this consistent runoff? Well, the first thing to look for is soil test phosphorus, right? How much phosphorus is in the soils? I'm saying there's a large source. Because we know as soil test phosphorus increases, we get increased dissolved phosphorus runoff. And then we can go and look at the Ohio Phosphorus Task Force report and see that, well, you know, if you look at Western Lake Erie Basin here, and Malik 3 is between 25 and 50 ppm, which is yearly about where we recommend phosphorus to be able to grow a successful crop in Ohio, right? So this doesn't indicate that we have extraordinarily high soil test phosphorus. We do around Grand Lake St. Mary's, but we also know that they have a history of application of manure that's built up the soils, and that's issue. Not seeming like that's happening here in Western Lake Erie. But we can also look more closely at, well, what are the main phosphorus inputs into Western Lake Erie Basin? Luckily, there's been some work on this to look at, well, where are the different sources coming from? Unfortunately, they named all the watersheds by a number, so I have to identify them for you. So this box here is Western Lake Erie Basin. Here's Cuyahoga, right? So we've got yellow is what you see here. Yellow is inorganic phosphorus fertilizer application. Brown is animal phosphorus loading. That's the manure phosphorus, right? And you can see it's really high over here. Those are the Grand Lake in Ohio, or the Grand River in Ontario. You know, I never say that very often, so it comes out as Grand Lake St. Mary's in Ohio. That's not what I meant at all. And then the red is human phosphorus loading, where we have lots of point sources. Cuyahoga fits in really well. Here's some other urban areas here as well. Okay, so looks like it's inorganic phosphorus fertilizer. That's what we should be looking at. And so when we put it together, we're like, well, phosphorus concentrations are not that high in soils. Everything's inorganic fertilizer. What could be happening here? And so what we've been looking into from our lab is the potential for phosphorus stratification. So what happened is, you know, in the 80s, when we decided that we needed to control more phosphorus coming off of the land, we started to focus a lot on soil erosion. So don't do more bowl plowing anymore, and instead do a conservational no-till. Today it's rotational no-till. So we don't turn the soil over so much with every crop anymore. We leave residue on the field so that we maintain some soil organic matter. What we think has happened is that buildup of residue, along with increased use of broadcast fertilizer application without turning the soil over, has led to phosphorus stratification in the soils. So if you took this soil core, and the orange is phosphorus concentrations, all the phosphorus is at the surface and it decreases with depth. So if you take that 0 to 8 inch core, you're not really doing an accurate job of looking at where phosphorus that's available to run off, what that concentration is. So why do we think this? This isn't something that was pulled out of the blue. There is a lot of research. Here's some work from Sharpley showing examples of phosphorus stratification in Pennsylvania soils. This is Malick here, really high, decreasing with depth into soil for a variety of different examples here. But a lot of his work has been looking at manure. You know, you surface apply manure and you see a lot of stratification. That's a thing. There's been some long-term field studies that have shown if you have no-till implemented, and you can see it was implemented here, we see big increases in dissolved phosphorus runoff over the years following that implementation. So continuous no-till can do this. So the big question for us is, well, do we see this develop when we have a rotational no-till, so it's not permanent no-till, and we're using commercial fertilizers instead of manure? And so we went to the Sandusky River watershed, monitored 1,500 fields, and indeed found stratification. So this is showing our results across all the fields. You know, this is going with depth into soil, so we have 0 to 1, 1 to 2, 2 to 5, and 5 to 8 inches. Here's Malick's, and you can see this decrease, general decrease in soil test as you move into depth in the soil. So I put the median here, so where these lines would be, so you can see how they compare. What you see is the top 1 inch is about 40% higher than the 0 to 8. If you turn that into the top 2 inches, it's more like 55% higher. So the question you can ask yourself is, well, is a 55%, 40 to 55% increase in soil phosphorus on the surface enough to increase dissolved phosphorus and runoff? We can do some back of the envelope calculations and say, well, if we turned all of this back into one number that's about 36 ppm, how much reduction would we expect to get in terms of reducing the risk for runoff? And that's about 28% with a 1 mole bore plow. That's pretty fast. That's a pretty quick possible fix if we just turn the soil over and mix it again. But we can also look at this variation. There's a lot of variation in phosphorus stratification too. It's not like there's just one number, right? So this is showing that 0 to 8 inch. So if you collected the whole core, what your number would be versus a 0 to 2 inch, what would be in the surface. And you can see there's a general increase. You know, this is the 1-to-1 line, so this is where you would expect them to be the same, but there's a whole lot of scatter here. So if you pick, say, around 40 ppm, you can't predict from this 40 ppm what your surface 2 inches would be. Maybe it's 40, maybe it's 110, right? There's a lot of variation there. So what we would suggest is if you're worried about phosphorus stratification, you just got to go out there and test it, because doing something like this, you can't just guesstimate what it would be. But all of this only matters if phosphorus is running off through tile drains in a way that we didn't really think about it before. So, we've always thought about phosphorus getting into tile drains as water slowly infiltrates and filters through the soil. What comes out doesn't have phosphorus in it. But there's increasing evidence, I think it's actually been around for quite some time, that a lot of the phosphorus that's getting into tile drains is going through preferential flow, going through macropores, these cracks and fissures that you can see in soil, root channels, earthworm holes, so that what's actually getting into the tile is very slightly slowed down or almost equivalent to surface runoff, which is, we know, can have high phosphorus concentrations. So some work from Doug Smith, who had been working in the St. Joseph River watershed before he moved to Texas, shows some of that, an example of that. So this is an edge of field site. You can see there was a rain event here. This was in May of 2011. Surface flow in black peaked. Tile flow peaked at the exact same time. Now, it has that same tail that you would expect out of tile flow as it slowly drains that field out. But what that means is that this water and this water is very, very similar, pretty much the same. So this is definitely a pathway for that phosphorus that's accumulating on the surface to make it into our waterways. And we'll see some work from Kevin Keene, so I'm going to steal a little bit of his thunder, hopefully not too much. But a lot of what he's showing is that an awful lot of dissolved phosphorus load is coming out of tile drains. And so this suggests that definitely that pathway is seeming to be true across a wide variety of different fields. However, what we're noticing is, these losses are not a huge amount. It's like 1% of what's being applied to a field. A lot of times these fields are in balance, so what's being taken out and what's being put in is about the same. So, and our phosphorus is at recommended levels. This really points to phosphorus has got to be in the wrong place. I think the other possible option is that phosphorus, what we think is an appropriate amount of soil test phosphorus for farming is not necessarily appropriate for environmental runoff, but I think Steve Coleman's going to tell us a lot about that tomorrow. So if we're up to me, first step in reducing dissolved phosphorus loss is to control phosphor stratification and improve our nutrient management. So with that, I just wanted to throw up a barrage of logos because we have a lot of supporters for all of our programs. I'm sure that those of you from some of these agencies could find yourself here, or you could pick out your favorite one. I'm sure some of them might be the Andersons instead of EPA or something, but that's fine. And if you have any other questions or want more information, we have lots of information here. I do want to highlight, we have a new website, so come and check out our new website. If you've been going to it and you're like, what happened to all your information? Well, we're slowly getting it onto ncwqr.org. So I think I have time for a few questions, maybe. Thoughts, comments? Over here.
You were looking at no-till there. Was that continuous no-till? We sometimes have an issue where we say, well, no-till, and then we go to, well, I no-till this year, but next year I work it. And
Yeah.
For me, that's kind of skip-a-till type instead of
Yeah. Yeah, so all of the measurements we made were rotational no-till. Now, of course, when you collect a soil test sample, it tends to be after your no-till year, right, because it's after soy, but before corn. But a lot of the farms that we had, they still work the ground some every rotation anyway. It's just whether they were doing a chisel or disc kind of thing. So that's why I wanted to look at it, in part because you hear this a lot for long-term no-till sites, but we're seeing this a bit also in rotational. I think it's because the soil's not being turned over. Jim?
What's the best way to reduce preferential flow?
To reduce preferential flow? It depends on who you talk to, but I'm hoping that it's an increase in soil organic matter. And if that works, then, and then we can increase water holding capacity, I think we could make a lot of progress. So I would call that a second step. First step is getting phosphorus off the surface and seeing if you have stratification, and another step, of course, is that. The other thing to think about, because we're going to be talking about practices a lot over the next 2 days, we have to remember that there are reasons to do things that aren't necessarily always just dissolve phosphorus. Improving yields and improving soil health and doing all of those sorts of things are also important too, and there shouldn't be a one-size-fits-all for everything. That's what I think, so, yeah. Over here.
How are you comparing the basins of your surface flow and your tile? Are they the same area, or are they?
So that is a Kevin Keene question. I believe that they are very similar, or at least they are accounted for. Does that sound right, Libby? They're accounted for. Yeah. Yeah, I know that when he goes to pick a field, if he can't get, say, a tile that is only draining a known area, then usually they don't instrument that field. Yeah.
In the course of the studies, have you taken into effect the difference in the amount of sulfur that's falling out of the atmosphere that we used to get for free, that now we have to supplement? I mean, that's certainly a change in the environment that's happened in that time.
Right, yeah, so, that's usually attributed to changes in precipitation pH with essentially remediating acid rain, and that is something that needs to be studied more. We have looked at sulfate runoff in our water, and we don't see any changes over that period of time, but that's not a huge surprise because we have a big geological source of sulfur. So sulfate runoff is basically driven by weathering rather than what's happening on a field-to-field basis. So I don't think we would capture it there. And we've looked at soil pH from soil test labs over that period of time. We don't see it there either, but I'm also not convinced that that test would be sensitive enough to necessarily pick up on that type of a change either. So there has been some studies from Doug Smith as well where he's taken soils from different places and extracted them using precipitation from the mid-1990s versus precipitation from today to see if you get a lot of dissolved phosphorus runoff. And it sounds like some soils you get it and some soils you don't. So there's a little bit of variation, and he's still working on trying to be able to predict why we see it in some and not in the others. So it's definitely something being looked into right now.
Is there a lot of within-field variability in terms of stratification?
Yes, there is. We did do some gridded sampling with the soil stratification, and what was kind of interesting, though, is that we looked at the combination of the variation in soil tests, because we were like, well, there could be a lot of variation just in soil test phosphorus within a field, and there was some, especially we had one field where there was an old barn, so you could see higher soil tests around where that used to be. But we found much, much higher variation in stratification, that it was really difficult to predict what area would have higher stratification than others. So, yeah.
You showed the graph that had the losses by fertilizer. And that's been, thrown up there a lot. You were basically saying the Western Lake Erie Basin had a lot of inorganic fertilizers, synthetic fertilizers.
It was actually input, so it was going into the basin. They weren't actually looking at the losses necessarily. Yeah, so that's an important difference, yeah.
All right, okay, so that kind of answers my question, maybe that, can we show whether inorganic or organic, which one loses easier, which one travels easier, or is there a difference?
So, in reality, there's not a huge difference. The way that manure is managed is different than commercial fertilizers because you're usually applying it because you want to get rid of it. It's a waste product. You need to do something with all of it. Whereas commercial fertilizers you're paying for, so you're putting it on at a very specific rate. Those differences make it so that fields that get manure have a higher possibility of having higher losses. But if manure and inorganic fertilizers are put on at the same rate, those studies have not shown big differences in phosphorus loss. But we are working with a couple of different folks that are working on fingerprinting of phosphorus to see if we can tell where it's coming from using a variety of different methods to say, well, what we actually see out of the end of the watershed, can we tell if it's mostly manure or inorganic or point sources or something else, and how does that change from low flow to high flow? So, but it's tough. I mean, phosphate's phosphate by the time it gets to us. Yeah. Over here, Jim.
Do natural systems ever stratify?
They do, yeah. I mean, that's kind of how natural soils work, right? When you think of a soil system. What I have not been able to find, because I've been trying to determine what possible levels of phosphorus there are. I mean, total phosphorus is clearly higher in an agricultural system. Malic phosphorus, most people studying forests don't measure malic, right? And whether those stratification levels are particularly high or not. But normally natural systems are not tiled either. and runoff, how water moves through that hydrologically is quite a bit different as well. Go ahead.
You mentioned preferential flow. How much do tile risers, surface inlets to the tile influence the watersheds?
So I consider a tile riser to be like the ultimate macropore, right? Because it's basically, that's its whole goal, is to not let that water pond and slowly infiltrate through the soil. So having a blind inlet, there's been some studies that have shown that that has a lot of promise to be very, very helpful. Most farmers prefer them if they can put them in, because you don't have to go around the riser. You can still farm right over it, and it's less hassle to deal with. So if you have any, I would encourage people to replace them with blind inlets if you can. Steve?
Yeah, if I can get this frog out of my throat. We talk about preferential flow as if it is one thing.
Yeah.
And I look at that picture that you showed that is also in Kevin King's presentation of the cracking.
Yeah.
We have a couple different situations. I mean, in long-term continuous no-till, we develop earthworms, which are preferential flow. Soil cracking is going to be much more severe in a conventionally tilled, bare surface soil than it is in a no-till field that has residue, which holds the moisture, which prevents the cracking. So, you know, we tend to throw everything into one bucket, but it's a little more complicated than that.
Yeah, yeah. I assume, did everybody hear that okay? Yeah, okay. Is that good?
Laura, on your stratification,
Yes.
you said all your studies was on mixed till. You didn't do
Yeah.
any continuous no-till sites?
We did have some. It was about 8% of the soils we collected. Same thing with manure. We didn't see any strong differences. It's kind of hard to compare when you have a huge amount of variation from your rotational no-till and then, you know, just a few fields to compare, but it wasn't drastically different. So most of the stratification was, you know, there was still stratification there. It wasn't like it was not there. It wasn't like it was always super high compared to a rotational no-till.
Were most of these fields in broadcast applications, or were some of them in banding on this?
60-40, 60% broadcast and then 40% we're doing banding for corn. Yep. Good. Thanks, everyone.
Thank you very much, Laura. Great presentation.